the vast cosmos lies a centuries-old mystery. Why is the night sky dark despite countless stars? On a moonless night, away from city lights, the Milky Way stretches overhead, a shimmering band of stars that has inspired generations. Yet this band represents just a fraction of the galaxy's hundreds of billions of stars. If you feel that same tension, that pull towards something we're not supposed to see, hit like, subscribe, and comment your thoughts. And if you want others to join us on this journey, share the video, X, Facebook, Reddit, anywhere you can. You're the reason stories like this reach beyond the algorithm. Thank you for being awake. This paradox, known as Olbers's paradox, challenges our understanding of the universe. The answer lies in the universe's nature and age. Born from the Big Bang approximately 13.8 billion years ago, light from distant stars takes billions of years to reach us. The most distant observed galaxy, GNZ11, is seen as it appeared 400 million years after the Big Bang, its light journeying over 13 billion years. This cosmic journey is further delayed by the universe's expansion, first observed by Edwin Hubble in the 1920s. As galaxies move away, their light stretches into longer wavelengths, a phenomenon called redshift. GNZ11 has a redshift of 11.09, meaning its light has stretched to over 12 times its original wavelength. The night sky's darkness reflects the universe's finite age and ceaseless expansion. Beyond the observable universe, spanning 93 billion light-years, lies the unknown. This expansion is driven by dark energy, a mysterious force comprising roughly 68% of the universe's energy content. Dark energy opposes gravity, pushing space apart at an ever-increasing rate, defying our understanding of space-time. The cosmos is a tapestry of paradoxes, from star birth to the enigmatic pull of dark matter and energy. Stars form in dense, cold, molecular hydrogen clouds like the Orion Nebula, yet for every star, there is far more invisible dark matter, outweighing ordinary matter 5-1. Dark matter's presence is inferred through its gravitational influence, shaping the universe's structure and holding galaxies together. Despite its critical role, dark matter remains undetectable, except through its gravitational effects. As we peer deeper into the abyss, we confront not just the mysteries of space, but the limits of human comprehension. How did the universe begin, and how will it end? Are we alone, or are there other forms of life among the stars? These questions inspire us to explore, building telescopes like the James Webb Space Telescope and searching for distant signals through projects like Breakthrough Listen. In the night sky's darkness, we find not emptiness, but possibility, a universe waiting to be explored and understood. Part 1. The Dark Sky Paradox. Why, in an infinite universe filled with stars, do we see darkness? The question is not merely philosophical, it strikes at the heart of our understanding of the cosmos. The paradox, first articulated by Heinrich Wilhelm Olbers in the 19th century, seems to defy intuition. If the universe is truly infinite and filled with an endless array of stars, every line of sight should eventually intersect with the surface of a star. The night sky, then, should be ablaze with light, a blinding tapestry of brilliance. Yet, when we look up at night, we are greeted by a vast expanse of darkness, speckled with only a few thousand stars visible to the naked eye. Olbers's paradox haunts us. If the cosmos is endless, every line of sight should eventually intersect a star. Yet the night sky is a canvas of black, punctuated by scattered points of light. The Milky Way, our home galaxy, contains between 100 billion and 400 billion stars. But even this staggering number is dwarfed by the estimated 2 trillion galaxies in the observable universe. Each of these galaxies, in turn, contains billions of stars, creating a cosmic landscape that seems incomprehensible in its scale. Observation. The universe is not static. Light from distant stars hasn't reached us yet, constrained by its finite speed. Light travels at approximately 299,792 kilometers per second speed. That seems instantaneous on human scales, but becomes a limiting factor when considering the vastness of the cosmos. The most distant objects we can observe, such as the cosmic microwave background, CMB, are over 13 billion light-years away, meaning their light has been travelling for nearly the entire age of the universe. Interpretation. The universe has a finite age, 13.5 billion years, and is expanding. This expansion, first observed by Edwin Hubble in the 1920s, means that galaxies are moving away from each other at staggering speeds. Distant light is stretched into invisibility, shifted into the infrared and radio bands by cosmic expansion. This phenomenon, known as redshift, is a direct consequence of the universe's expansion. As light travels through space, the wavelength of the photons is stretched, shifting their color toward the red end of the spectrum, for light from the most distant. Galaxies, this shift is so pronounced that it moves beyond the visible spectrum entirely, rendering these galaxies invisible to human eyes and most telescopes. Speculation. Could there be regions of space where light has yet to reach us, hidden beyond the cosmic horizon? The observable universe, the region of space from which light has had time to reach Earth, is estimated to be 93 billion light-years in diameter. However, this represents only a fraction of the entire universe, which may be infinite in size. Beyond the cosmic horizon lies a realm that is, by definition, unobservable. Light from these regions has not yet had time to reach us, and the expansion of the universe ensures that some of these regions may never be visible to us. The darkness of the night sky is not an absence, but a testament to the universe's dynamic nature. It is a reminder that the cosmos is not a static, unchanging entity, but a living, breathing system governed by the laws of physics. The darkness of the night sky also raises questions about the distribution of matter and energy in the universe. If the universe were truly homogeneous and isotropic, the same in all directions, the paradox would be even more pronounced. However, the universe is clumpy, with matter unevenly distributed across vast scales. Galaxies are not spread evenly, but are clustered in filaments and sheets separated by vast voids. These voids, some spanning hundreds of millions of light-years, are largely devoid of matter and contribute to the darkness we observe. The cosmic web, as it is known, is a vast, interconnected structure of galaxies, gas clouds, and dark matter, all held together by the gravitational forces that shape the universe. The paradox also touches on the nature of light itself. Light, while seemingly eternal, is subject to the same physical laws as everything else in the universe. It can be absorbed, scattered, or blocked by interstellar dust and gas, further reducing the amount of light that reaches our eyes. The interstellar medium, the space between stars, is not empty but filled with a tenuous mixture of gas, dust, and plasma. This material, though sparse, can have a cumulative effect over cosmic distances, dimming the light from distant stars and galaxies. The implications of Olber's paradox extend beyond the visible universe. The same principles that explain the darkness of the night sky also apply to other forms of radiation, such as X-rays and gamma rays. The cosmic X-ray background, a faint glow of X-rays permeating the universe, is a remnant of the most energetic events in cosmic history, such as supernovae and active galactic nuclei. Similarly, the cosmic neutrino background, a theoretical sea of neutrinos left over from the Big Bang, is another form of radiation that fills the universe. These background radiations, while undetectable to human senses, are a testament to the universe's dynamic nature and the ongoing processes that shape it. The mystery deepens. What lies beyond the observable universe hidden from our sight? The cosmic horizon, the boundary of the observable universe, is not a physical barrier, but a limit imposed by the bold speed of light and the age of the universe. Beyond this horizon lies a realm that is forever beyond our reach, a cosmic wilderness that we can only speculate about. The universe's expansion, driven by the mysterious force known as dark energy, ensures that some regions of space will never be visible to us. As the universe continues to expand, the cosmic horizon will grow, revealing more of the universe to our instruments. However, the expansion also means that some regions will recede from view, their light forever lost to the void. In this context, the darkness of the night sky is not just a scientific curiosity, but a profound philosophical question. It challenges our understanding of the universe and our place within it. It forces us to confront the limits of our knowledge and the vastness of the cosmos. The darkness is a reminder of the universe's infinite possibilities and the mysteries that lie beyond our reach. It is a testament to the ongoing quest for understanding, a quest that has driven human curiosity since the dawn of civilization. As we continue to explore the cosmos, the darkness of the night sky will remain a constant companion, a symbol of the unknown and a beacon of discovery. Part 2. The missing antimatter. Where did all the antimatter go? This question haunts cosmologists, a lingering mystery that challenges our understanding of the universe's birth. The Big Bang, the explosive event that marked the beginning of space and time, should have produced matter and antimatter in perfect equilibrium. Every proton should have had an antiproton counterpart, every electron a positron, every neutron an antineutron. Yet, as we scan the cosmos, we find a universe overwhelmingly dominated by matter. Stars, galaxies, planets, and even the atoms that comprise our bodies are built from matter, with antimatter appearing only in fleeting traces. If matter and antimatter had been created in equal amounts, the universe would have been a vast, featureless expanse of pure energy, devoid of structure or life. The fact that we exist at all is a testament to the profound imbalance that tipped the cosmic scales in favor of matter. Observation. Antimatter is exceedingly rare, detected only in high-energy environments like cosmic rays or the violent collisions of stars. When matter and antimatter meet, they annihilate in a burst of pure energy, a spectacle captured in particle accelerators like the Large Hadron Collider. However, these events are isolated and transient, starkly contrasting with the vast, stable structures formed by matter. The cosmic microwave background. Radiation, the afterglow of the Big Bang, reveals a universe that cooled and expanded, but it carries no trace of the annihilation that should have occurred if matter and antimatter were equally abundant. Instead, it paints a picture of a universe that somehow avoided total destruction, preserving the building blocks of galaxies, stars, and eventually life. Interpretation. The asymmetry between matter and antimatter suggests that a fundamental imbalance existed in the early universe. Theories proposed that violations of fundamental symmetries, charge, c, parity, p, and time, t, could explain this discrepancy. In 1964, physicists James Cronin and Val Fitch discovered that certain particles known as kaons could decay in a way that violated CP symmetry. This groundbreaking observation earned them the Nobel Prize in Physics in 1980 and provided the first experimental evidence that the laws of nature are not perfectly symmetrical. However, the CP violation observed in kaons and later in B mesons is insufficient to account for the matter-antimatter asymmetry observed in the universe. The imbalance must have been more pronounced, perhaps driven by processes that occurred in the first fractions of a second after the Big Bang. Theories extend to the realm of leptogenesis, where heavy, unstable neutrinos in the early universe could have decayed asymmetrically, producing more matter than antimatter. This process, occurring just after the Big Bang, would have established the imbalance that persists today. Imagine a universe just 10 hours 12 seconds old, a seething cauldron of energy where neutrinos, the ghostly particles that barely interact with matter, played a pivotal role. As these heavy neutrinos decayed, they could have produced slightly more matter particles than antimatter particles, setting the stage for the cosmos we inhabit. Another theory, known as baryogenesis, suggests that interactions between quarks and antiquarks during the universe's rapid expansion could have favored the creation of matter. These ideas remain speculative, requiring further experimental validation, but they offer tantalizing glimpses into the universe's earliest moments. Speculation: did the asymmetry arise spontaneously during the Big Bang, or was it a precursor to the event itself? Some physicists proposed that the universe began with a slight excess of matter, a seed of asymmetry that amplified as the universe expanded. This seed could have been as small as one extra particle in a billion, yet it would have been enough to tip the balance in favor of matter. Others suggest that the Big Bang was not a singular event, but part of a cycle of cosmic creation and destruction, with matter-antimatter. A symmetry emerging over countless iterations. These ideas push the boundaries of our understanding, challenging us to rethink the fundamental nature of reality. Perhaps the universe is just one in a multiverse of possibilities, where the laws of physics vary from one realm to the next. The absence of antimatter is not just a cosmic curiosity, but a profound riddle that hints at unknown laws of physics. It forces us to confront the limits of our knowledge and inspires new theories that could revolutionize our understanding of the universe. The search for antimatter extends beyond Earth, with satellites like the Alpha Magnetic Spectrometer, AMS, installed on the International Space Station scanning the cosmos for antimatter signatures. Since its installation in 2011, AMS has detected over 100 billion cosmic rays, yet antimatter remains elusive, appearing in less than 1 in a million events. Each detection is a fleeting glimpse of a universe that could have been, a reminder of the annihilation that defines the boundaries between matter and antimatter. The matter-antimatter asymmetry is not merely a theoretical puzzle, but a critical gap in our understanding of the universe's origins. It touches on the most profound questions of existence. Why are we here? Why is the universe structured the way it is? The quest to solve this riddle drives physicists to explore the boundaries of the known universe, from the smallest subatomic particles to the vast, uncharted expanses of space. Each new experiment, each new observation brings us one step closer to unraveling the mystery of the missing antimatter, and perhaps to understanding the very nature of reality itself. As we peer deeper into the cosmos, we are not just searching for antimatter, We are searching for the reason behind our own existence. Part 3. The Unseen Mass. What holds galaxies together? The answer lies not in the luminous stars, gas and dust that we see, but in something far more mysterious. In the 1930s, Swiss astronomer Fritz Zwicky studied the Coma Cluster, a massive congregation of over 1,000 galaxies some 320 million light-years away. He observed that the galaxies were moving too fast to be held together by the visible matter alone. The cluster should have torn itself apart, yet it remained intact. Zwicky proposed the existence of dunkle Materie, dark matter, to explain this discrepancy. His work was met with skepticism, but it laid the groundwork for a revolution in cosmology. Decades later, Vera Rubin and Kent Ford confirmed Zwicky's findings on a galactic scale. Observation. They measured the rotation curves of spiral galaxies, expecting to find that stars farther from the center moved slower, as predicted by Newtonian gravity. Instead, they found that stars on the outskirts moved just as fast as those near the core. This defied conventional physics. Interpretation: an unseen mass, dark matter, must be providing the extra gravity to hold these galaxies together. Rubin's work was a turning point, transforming dark matter from a fringe idea into a cornerstone of modern astrophysics. Dark matter's influence extends far beyond individual galaxies. It is the scaffolding of the universe. Shaping the cosmic web of galaxy clusters and superclusters, simulations of cosmic structure formation show that without dark matter, galaxies would never coalesce. The universe would look vastly different, a thin, uniform soup of particles lacking the rich tapestry of stars, galaxies, and nebulae we see today. Yet, despite its pivotal role, dark matter remains invisible to telescopes, interacting only through gravity. The hunt for dark matter particles has become one of the most ambitious quests in science. Speculation. Could dark matter be composed of weakly interacting massive particles, WIMPs, elusive entities that barely interact with normal matter? Or could it be made of axions, hypothetical particles far lighter than electrons, created in the aftermath of the Big Bang? Experiments like the Large Hadron Collider, LHC, and the Xenon project have searched for WIMPs, while the axion dark matter. Experiment ADMX seeks to detect axions. So far, these efforts have yielded no definitive results, leaving dark matter's identity as enigmatic as ever. One intriguing possibility is that dark matter might not be a single type of particle but a mix of different components. Some theories propose that dark matter could include primordial black holes, remnants from the early universe, or even exotic particles like gravitinos predicted by supersymmetry. Others suggest that dark matter might interact with ordinary matter in ways we haven't yet considered, through forces beyond the standard model of particle physics. These ideas push the boundaries of our understanding, challenging us to rethink the fundamental nature of the cosmos. Dark matter's existence is not just a theoretical curiosity. It has profound implications for the fate of the universe. It makes up approximately 27% of the cosmos, outweighing ordinary matter by more than 5 to 1. Its gravitational pull shapes the distribution of gas and dust, influencing star formation and galaxy evolution. Without dark matter, the universe would lack the structure and complexity we observe. Yet its true nature remains hidden, a ghostly presence that eludes our best efforts to pin it down. As astronomers continue to map the cosmos, they uncover more evidence of dark matter's pervasive influence. The Bullet Cluster, a system of 2 colliding galaxy clusters, provides one of the most striking examples. Observations show that the visible matter, stars and gas, has separated from the gravitational mass, which remains concentrated in two distinct regions. This separation is direct evidence of dark matter's existence, as the gravitational mass cannot be explained by visible matter alone. Such observations reinforce the idea that dark matter is not just a theoretical construct, but a real, tangible component of the universe. The search for dark matter is a global endeavor involving scientists from every corner of the world. Deep underground, in facilities like the Gran Sasso National Laboratory in Italy and the Sanford Underground Research Facility in the United States, detectors wait patiently for a signal, a rare interaction between dark matter and ordinary matter. In space, satellites like the Fermi Gamma Ray Space Telescope scan the cosmos for signs of dark matter annihilation, a process that could produce detectable gamma rays. Each experiment adds another piece to the puzzle, bringing us closer to unraveling the mystery of the unseen mass. Dark matter's existence is confirmed by gravitational effects, but its composition remains unknown. Its elusive nature continues to challenge our understanding of the universe, driving us to explore new theories and technologies in the quest to unmask the cosmos. Part 4. The Accelerating Universe. Why is the universe expanding faster? In the late 20th century, astronomers made a discovery that upended our understanding of the cosmos. Distant supernovae, those cataclysmic explosions of dying stars, revealed a startling truth. The universe's expansion is not slowing down under the pull of gravity, as expected, but accelerating. Observation: Type Ia supernovae, which all explode with nearly identical brightness, appeared dimmer than expected. When observed in distant galaxies, this dimness is not due to any intrinsic difference in the supernova themselves, but because they are farther away than predicted by a universe expanding at a constant or decelerating rate. Interpretation: These observations suggest that some unseen force dubbed dark energy is counteracting gravity, pushing galaxies apart at ever-increasing speeds. The implications of this discovery are staggering. In 1998, two independent teams of researchers, one led by Saul Perlmutter at the Lawrence Berkeley National Laboratory, and the other by Brian Schmidt and Adam Rees, analyzed data from dozens of Type Ia supernovae and reached the same conclusion. The universe's expansion is accelerating. This finding earned them the Nobel Prize in Physics in 2011, underscoring the significance of their work. Today, dark energy is estimated to make up approximately 68% of the total energy content of the universe, dwarfing the contributions of ordinary matter about 5% and dark matter about 27%. Speculation: Could dark energy's properties change over time, leading to a future contraction or even a big rip? Some theoretical models suggest that dark energy might not be constant, but instead could evolve, growing stronger or weaker as the universe ages. In one scenario, known as the Big Rip, dark energy becomes so dominant that it tears apart not just galaxies and stars, but even atoms, leading to the complete dissolution of the universe. However, this remains purely speculative, as current observations provide no evidence for such a dramatic outcome. The fate of the universe hinges on this enigmatic force, shaping the cosmos on the grandest scales. Dark energy's influence extends beyond the motion of galaxies. It determines the ultimate destiny of the universe itself. If dark energy remains constant, the universe will continue to expand indefinitely, growing colder and more diffuse until it reaches a state of near emptiness known as the heat death of the universe. Alternatively, if dark energy weakens or disappears, gravity could eventually slow and reverse the expansion, leading to a cosmic contraction and a potential big crunch. Dark energy's nature is unknown, but its influence dominates the universes. Expansion. Despite its pivotal role, scientists have yet to identify what dark energy is or how it operates. Some theories propose that it is a property of empty space itself, a kind of vacuum energy that permeates the entire universe. Others suggest it could be a dynamic field similar to the Higgs field that interacts with matter and energy in subtle ways. To deepen our understanding, astronomers are turning to increasingly sophisticated tools. The Dark Energy Survey, DES, for example, has mapped hundreds of millions of galaxies across vast swathes of the sky, providing unprecedented detail about the distribution of matter and energy in the universe. The upcoming Euclid mission, led by the European Space Agency, aims to refine these measurements even further, using a combination of visible and near-infrared light to study the effects of dark energy on cosmic structures over billions of years. The search for answers continues in the farthest reaches of the cosmos. By studying the light from distant supernovae, quasars, and even the faint echoes of the Big Bang itself, researchers hope to unravel the mysteries of dark energy. Each new observation brings us closer to understanding the forces that govern the universe's fate, from the smallest particles to the largest cosmic structures. The journey is far from over, but with every step, we inch closer to solving one of the greatest mysteries in science: the nature of the accelerating universe. Part 5. The Cosmic Web. How is the universe structured? Galaxies are not scattered randomly but are woven into a vast cosmic web, a tapestry of unimaginable scale and complexity. This intricate structure spans hundreds of millions of light-years, dwarfing the distances between individual galaxies. Observation. Large-scale surveys like the Sloan Digital Sky Survey, which has mapped over 3 million galaxies and quasars, reveal an interconnected network of threads, nodes, and voids. These threads are immense filaments of galaxies stretching across the cosmos, while nodes are dense clusters where filaments intersect. The largest of these nodes, such as the Virgo supercluster, can contain thousands of galaxies and span tens of millions of light-years. Voids, on the other hand, are vast, empty regions that occupy up to 80% of the observable universe, some stretching over 200 million light-years in diameter. One of the most notable voids, the Bhuta's void, is nearly 330 million light-years across, a desolate expanse where the scarcity of galaxies challenges our understanding of cosmic formation. Interpretation. The cosmic web is the result of gravity amplifying tiny density fluctuations from the early universe. These fluctuations, originating from quantum ripples in the primordial plasma, grew over billions of years as matter clumped together under the influence of gravity. Filaments formed along the boundaries of these fluctuations, while voids expanded in the empty spaces between them. This process is ongoing, with galaxies continuing to migrate along filaments towards the nodes, driven by the relentless pull of gravity. For example, the Milky Way and the Andromeda Galaxy are on a collision course, destined to merge in about 4.5 billion years, illustrating the dynamic nature of the cosmic web. These mergers not only reshape the web, but also trigger bursts of star formation, as gas and dust are compressed and ignited by the gravitational interactions. Speculation. Could the distribution of dark matter explain the web's structure? Dark matter, which makes up approximately 27% of the universe, provides the gravitational scaffolding for the cosmic web. Its unseen tendrils shape the paths of galaxies and determine the locations of filaments and nodes. However, the nature of dark matter remains unknown, leaving its role in the web's formation shrouded in mystery. Some theories suggest that dark matter's interactions with itself, or with ordinary matter, could influence the web's evolution in ways we are only beginning to understand. For instance, if dark matter particles are self-interacting, they could create additional clumping or smoothing effects, altering the distribution of galaxies in ways that current models do not fully account for. The cosmic web is a fossil record of the universe's infancy, a blueprint of creation. It preserves the imprint of the early universe's density fluctuations, which were frozen into place when the cosmic microwave background radiation was released 380,000 years after the Big Bang. By studying the cosmic web, astronomers can peer back in time, deciphering the conditions that shaped the universe we see today. This web is not static. It is dynamic, evolving as galaxies merge, filaments thicken, and voids expand. Over billions of years, the cosmic web has transformed from a faint sketch into a masterpiece of cosmic architecture. Astronomers now use supercomputers to simulate the evolution of the cosmic web, tracking the movements of billions of virtual particles to recreate the web's formation. These simulations, such as the Illustrious project, reveal how the cosmic web structure depends on the interplay between dark matter, gas, and stars. The cosmic web structure is mapped, but its origins remain tied to the mysteries of dark matter. While surveys like the Sloan Digital Sky Survey and the upcoming Legacy Survey of Space and Time, LSST, at the Vera C. Rubin Observatory, will refine our understanding of the web's structure, the fundamental questions about its formation remain unanswered. The LSST, slated to begin operations in the mid-2020s, will catalogue billions of galaxies over a decade, providing an unprecedented dataset to probe the web's fine details. This data could reveal subtle patterns in the distribution of galaxies that might hint at the properties of dark matter, or even the influence of dark energy on the web's expansion. The cosmic web is a testament to the universe's interconnectedness, a reminder that even the most distant galaxies are part of a grand, unified design. As we continue to explore its depths, we edge closer to unraveling the secrets of the cosmos itself. For instance, the discovery of the largest known structure in the universe, the Hercules Corona Borealis Great Wall, a filament stretching over 10 billion light-years, challenges our understanding of how such massive formations could arise in a universe dominated by dark energy. These enigmatic structures may hold the key to unlocking the full story of the cosmic web. Part 6. The Echo of Creation. What is the cosmic microwave background? A faint, uniform glow permeates the universe, the cosmic microwave background. It is an ethereal whisper from the dawn of time, invisible to the human eye but detectable by sensitive radio telescopes. Observation. Discovered accidentally in the 1960s by Arno Penzias and Robert Wilson at Bell Labs. It is the oldest light in the universe, a relic from a time when the cosmos was just 380,000 years old. This radiation, with a temperature of just 2.7 degrees above absolute zero, bathes every corner of the observable universe, a silent testament to its fiery origins. Interpretation. This radiation is an echo of the Big Bang, released when the universe was still a seething plasma of electrons and protons. It marks the moment when the universe became transparent, allowing photons to travel freely through space for the first time. Speculation: could tiny fluctuations in the background hold clues to the universe's future? These subtle variations, on the order of 1 part in 100,000, are believed to be the seeds from which galaxies and stars would later form. The cosmic microwave background is a snapshot of the universe's infancy, encoding secrets of its evolution. The detection of the cosmic microwave background was a revolution in cosmology. It provided the first direct evidence of the Big Bang. Theory, which had been proposed by Georges Lemaitre in 1927 and expanded upon by George Gamow in the 1940s. Before this discovery, the idea of an expanding universe was still debated, with some scientists favoring a static, unchanging cosmos. However, the uniformity and temperature of the background radiation aligned perfectly with predictions made by the Big Bang model, effectively settling the debate. In 1989, the Cosmic Background Explorer, COBE, satellite mapped the cosmic microwave background with unprecedented precision, revealing faint ripples that corresponded to slight fluctuations in the density of the early universe. These fluctuations, magnified over billions of years, would eventually give rise to the vast structures we see today: galaxies, clusters, and superclusters. The cosmic microwave background confirms the Big Bang theory, but raises new questions about the universe's structure. For instance, the uniformity of the background radiation poses a profound mystery. How could regions of the universe that were never in causal contact, that is, never able to exchange information, have the same temperature? This question, known as the horizon problem, remains one of the most intriguing puzzles in cosmology. Additionally, the faint ripples in the background radiation suggest that the universe was not perfectly smooth in its early stages. These imperfections, though minuscule, were enough to set the stage for the formation of large-scale structures. However, their origin remains unclear. Were they random quantum fluctuations magnified by the rapid expansion of the universe? Or do they hint at deeper, unknown processes at work? To study the cosmic microwave background, scientists have launched increasingly sophisticated satellites and ground-based observatories. The Wilkinson microwave anisotropy probe, WMAP, launched in 2001, provided a detailed map of the background radiation, revealing that the universe is approximately 13.8 billion years old. This map also confirmed that ordinary matter, the stuff that makes up stars, planets, and people, accounts for only about 5% of the universe's total mass-energy content. The rest is composed of dark matter, about 27%, and dark energy, about 68%, two mysterious substances whose nature remains poorly understood. In 2009, the Planck satellite was launched to study the cosmic microwave background with even greater precision. Its findings have refined our understanding of the universe's composition and structure, but they have also deepened the mystery of its origins. The cosmic microwave background is more than just a relic of the past. It is a living document of the universe's history. Its faint glow carries information about the earliest moments of creation, when the laws of physics as we know them were still taking shape. By studying this ancient light, scientists hope to unlock secrets about the nature of space and time, the behavior of matter and energy, and the ultimate fate of the cosmos. Yet, for all its revelations, the cosmic microwave background remains an enigma. It is a whisper from the edge of eternity, a message written in the language of the universe itself, waiting to be deciphered. Part 7. The Horizon Paradox. Why is the universe so uniform? The question is as profound as it is perplexing, a mystery that has pervaded cosmology since the early days of the field. The cosmic microwave background, CMB, the oldest light in the universe, is staggeringly uniform, even in regions so distant from one another that they couldn't have exchanged information since the Big Bang. This is the essence of the horizon paradox. How can parts of the universe that have never been in causal contact share such strikingly similar properties? Imagine two observers standing at opposite ends of the observable universe, separated by approximately 93 billion light-years. Despite this unfathomable distance, the temperature of the CMB they measure differs by less than 0.001%. This uniformity is akin to two strangers on opposite sides of the Earth having the exact same birth date, down to the second, without ever having communicated. Observation. The temperature variations in the CMB are minuscule, on the order of 1 part in 100,000. Imagine holding a perfect sphere in your hands, its surface smooth and unblemished, save for the tiniest ripples. This is the cosmic microwave background. These fluctuations, though slight, are the seeds from which galaxies, stars, and ultimately life emerged. Yet their uniformity defies conventional explanations. When the Planck satellite mapped the CMB with unprecedented resolution in 2013, it revealed intricate patterns in these fluctuations, including subtle anomalies that hint at physics beyond our current understanding. One such anomaly is the cold spot, a region of the CMB significantly cooler than its surroundings, which some theories suggest could be a remnant of a collision with another universe. The horizon paradox is not merely an academic curiosity, it is a fundamental challenge. To our understanding of the universe's earliest moments, to address it, cosmologists have proposed a theory as bold as it is elegant: cosmic inflation. This idea posits that the universe underwent a brief but explosive period of exponential expansion, stretching space itself at a rate faster than the speed of light. In a fraction of a second, roughly 10^32 seconds, the universe ballooned from a size smaller than a proton to a scale unimaginably vast. During this expansion, the fabric of space-time itself was stretched, smoothing out any irregularities and ensuring the uniformity we observe today. Interpretation. Cosmic inflation explains the uniformity of the CMB by ensuring that regions now far apart were once in close contact. During this expansion, quantum fluctuations, tiny variations in the energy density of the early universe, were stretched to cosmic scales. These fluctuations became the subtle temperature variations we observe today. Inflation also solves other puzzles, such as the flatness problem, which asks why the geometry of the universe is so close to being perfectly flat. The flatness problem is akin to balancing a pencil on its tip. Any slight deviation from perfect flatness would have caused the universe to collapse or expand chaotically. Inflation provides a mechanism for achieving this delicate balance. Yet, inflation is not without its mysteries. The theory suggests that the universe may have undergone multiple phases of inflation, each with its own unique characteristics. Some models even propose that our universe is but one of countless bubble universes within an ever-inflating multiverse. This multiverse, if it exists, would be a vast and varied landscape, with each bubble universe governed by its own laws of physics. In such a scenario, our universe could be just one of an infinite number of realities, each with its own unique properties and histories. Speculation. Could inflation have left detectable signatures in the cosmic microwave background? One such signature is gravitational waves. Ripples in spacetime caused by the rapid expansion of the universe during inflation. These waves, if detected, would provide direct evidence of inflation and offer a glimpse into the universe's earliest moments. The search for these primordial gravitational waves is one of the most active areas of modern cosmology. Unlike the electromagnetic radiation we typically observe, gravitational waves interact weakly with matter, making them difficult to detect. However, their faint signal could be embedded in the polarization of the CMB, a subtle twisting of light that traces the gravitational wave's passage through spacetime. The BICEP 2 experiment, announced in 2014, initially claimed to have detected these gravitational waves by observing the polarization of the CMB. However, subsequent analysis revealed that the signal was likely contaminated by dust from our own galaxy. The quest continues with ongoing experiments like the BICEP array and the Simons Observatory, poised to deliver new insights. These instruments, located in the high-altitude deserts of Antarctica and Chile, scan the sky with unprecedented precision, hunting for the subtle imprint of gravitational waves. In Antarctica, the BICEP array operates at the South Pole, where the cold, dry air minimizes atmospheric interference, allowing for exceptionally clear observations of the CMB. Meanwhile, the Simons Observatory in Chile's Atacama Desert uses an array of telescopes to map the CMB with unprecedented sensitivity, aiming to uncover the faint signals left by inflation, the Fermi Paradox. Though challenging, has spurred some of the most creative and ambitious ideas in cosmology. It has forced scientists to confront the limitations of their theories and to push the boundaries of what is observable. In doing so, it has deepened our understanding of the universe's origins and the fundamental laws that govern it. The paradox reminds us that the universe is not merely a collection of stars and galaxies, but a dynamic, evolving entity whose mysteries are as profound as they are beautiful. As we continue to explore the cosmos, the Fermi Paradox stands as a testament to the power of curiosity and the human desire to understand the unknown. Part 8. The Fate of the Universe. Will the universe expand forever? This question has haunted astronomers for decades, stirring debates and inspiring theories that stretch the boundaries of human imagination. The universe's fate hinges on the balance between matter, radiation, and dark energy, the mysterious force that permeates the cosmos and drives its expansion. Observation. Current observations, including data from the Hubble Space Telescope and the Planck satellite, suggest that the universe's expansion is not slowing down, but accelerating. This discovery, made in the late 1990s, earned the Nobel Prize in Physics in 2011 and revolutionized cosmology. The acceleration is subtle but measurable, with galaxies moving away from each other at an ever-increasing rate, like dots on a balloon being blown up. Interpretation. If dark energy continues to dominate, as it has for the past 6 billion years, the universe will expand indefinitely. This scenario, known as the Big Freeze or heat death, paints a bleak picture of the cosmos. Stars will eventually exhaust their fuel, galaxies will drift farther apart, and the universe will become a cold, desolate expanse. By roughly 100 trillion years from now, all stars will have burned out, leaving only black dwarfs, neutron stars, and black holes. The cosmos will be a graveyard of dead stars, with temperatures approaching absolute zero. In this frigid environment, even the faint glow of black holes evaporating through Hawking radiation will be the last vestige of warmth in an otherwise lifeless void. Speculation. Could dark energy's properties change over time, leading to a contraction or even a cyclical universe. Some theories propose that dark energy might weaken or reverse its effect, causing the universe to slow its expansion and eventually collapse in a big crunch. Alternatively, the universe could oscillate between expansion and contraction in an eternal cycle of cosmic rebirth. However, these ideas remain purely speculative, as current observations provide no evidence of such behavior. Dark energy's true nature remains one of the greatest mysteries in science. Some models suggest that dark energy could be a dynamic force, fluctuating in strength over cosmic timescales, though such hypotheses are difficult to test with existing technology. The ultimate destiny of the cosmos remains an open question, a cosmic riddle that challenges our understanding of physics and reality. Astronomers continue to refine their measurements of the universe's expansion rate, known as the Hubble constant, which currently stands at approximately 70 kilometers per second per megaparsec. Yet discrepancies between different measurement methods hint at potential new physics beyond our current models. For instance, observations of the cosmic microwave background radiation suggest a Hubble constant of around 16 Merthin s MPC, while measurements of nearby supernovae yield a value closer to 73 s MPC. This tension, if confirmed, could point to undiscovered forces or particles influencing the universe's expansion. Imagine a distant future where galaxies are but faint smudges in the cosmic void, their light dimmed by the relentless march of time and space. In this era, intelligent beings, if they exist, will gaze upon a universe devoid of the vibrant stars and galaxies we see today. The night sky will be a lonely expanse, with only the faintest glimmers of light from distant black holes and the dying embers of once great stars. This vision of cosmic isolation serves as a poignant reminder of the fragility and transience of existence in an ever-expanding universe. In this desolate epoch, the remnants of galaxies will be spread thin across trillions of light years, their once vibrant structures reduced to faint, diffuse clouds of particles and radiation. The quest to understand the fate of the universe is not merely academic. It speaks to humanity's deepest questions about existence, purpose, and the nature of reality. As we peer into the cosmos with ever more powerful telescopes and instruments, we are not just observing distant objects. We are glimpsing the story of our own origins and future. The universe's expansion, driven by dark energy, is a cosmic narrative that began with the Big Bang and will unfold over trillions of years. Whether it ends in a big freeze, a big crunch, or something else entirely, the fate of the universe is intertwined with our own, a testament to the interconnectedness of all things in the grand tapestry of existence. The search for answers continues with upcoming missions like the Euclid Space Telescope and the Vera C. Rubin Observatory, poised to shed new light on dark energy and the universe's destiny. These instruments will map the distribution of matter across vast swaths of the cosmos, probing the effects of dark energy with unprecedented precision. By studying the subtle warping of space-time caused by dark energy, astronomers hope to unravel its mysteries and finally answer the question: what is the ultimate fate of the universe? For now, the cosmos holds its secrets close, but with each new discovery, we inch closer to understanding our place in the grand cosmic drama. Part 9. The Black Hole Enigma. What lies within a black hole? The question has haunted scientists for decades, a cosmic riddle that defies easy answers. Black holes are regions where gravity overpowers all other forces, trapping even light in an eternal prison. They are the ultimate cosmic abyss, where the known laws of physics break down and the fabric of space-time itself is twisted into shapes that defy human comprehension. Observation: supermassive black holes reside at the hearts of galaxies such as Sagittarius A, the 4 million solar mass behemoth at the center of the Milky Way, some 26,000 light-years from Earth. These colossal entities, millions to billions of times the mass of the Sun, anchor entire galactic systems, their gravity dictating the orbits of stars and gas clouds across vast distances. Interpretation: black holes warp space-time, creating event horizons, boundaries beyond which nothing escapes. The event horizon is not a physical surface, but a point of no return, a one-way membrane where the gravitational pull is so intense that not even light, the fastest entity in the universe, can overcome it. Beyond this boundary, the laws of physics as we understand them cease to exist. Time slows to a crawl, and space is stretched into an infinite singularity at the center, a point of zero volume and infinite density. Speculation: could black holes connect to other universes through wormholes? This idea, though purely theoretical, suggests that the immense gravitational forces within a black hole might create shortcuts through space-time, bridging distant regions of the cosmos or even entirely separate universes. Such concepts push the boundaries of our imagination and challenge our understanding of reality itself. Black holes are laboratories for extreme physics, testing the limits of our understanding. They are nature's ultimate experiment, where the theories of general relativity and quantum mechanics collide in a maelstrom of contradictions. The immense gravitational forces at play within black holes compress matter into states that cannot be replicated in any earthly laboratory, offering physicists a glimpse into the most fundamental workings of the universe. Observation: in 2019, the Event Horizon Telescope, a global array of radio observatories, working in unison, captured the first ever image of a black hole, M1870C, a supermassive entity located 55 million light-years away in the galaxy Messier 87. This groundbreaking achievement provided visual confirmation of the event horizon, a feat once thought impossible. Yet the mysteries of black holes run deep. Observation: stellar mass black holes formed from the collapse of massive stars are scattered throughout the cosmos. These smaller but no less enigmatic objects are the remnants of stars that have exhausted their nuclear fuel, their cores collapsing under the weight of their own gravity. Interpretation: these black holes, ranging from a few to tens of solar masses, are often found in binary systems, where they orbit a companion star. The intense gravitational interaction between the black hole and its companion can lead to dramatic phenomena, such as the accretion of matter from the star onto the black hole, releasing enormous amounts of energy in the form of X-rays and gamma rays. Speculation: could these binary systems hold clues to the formation and evolution of black holes? Their study provides insights into the dynamics of gravitational collapse and the extreme conditions that give birth to these cosmic titans. Black holes are not merely passive entities, they actively shape the universe around them. Observation: active. Galactic nuclei, AGN, are the brightest objects in the universe, powered by supermassive black holes at the centers of galaxies. These AGN emit vast quantities of energy as matter spirals into the black hole, forming an accretion disk that glows with intense radiation. Interpretation: the jets of plasma and radiation that stream from these AGN can extend thousands of light-years into space, influencing the evolution of their host galaxies. Speculation. Could these jets play a role in regulating star formation, heating interstellar gas, and preventing it from collapsing into new stars? The interplay between black holes and their galactic environments is a complex dance of creation and destruction, a cosmic ballet that shapes the evolution of the universe. Black holes are confirmed by their gravitational effects, but their interiors remain hidden, despite decades of research and groundbreaking. Observations, the true nature of black holes remains shrouded in mystery. The singularity at the center of a black hole, where the laws of physics break down, is a conceptual chasm that challenges our understanding of the universe. As we continue to probe the depths of these cosmic enigmas, we inch closer to unraveling the fundamental secrets of existence itself. Black holes, in all their terrifying beauty, stand as a testament to the limits of human knowledge and the boundless potential of the cosmos. Part 10. The Information Paradox. Does information survive a black hole? Black holes, the enigmatic giants of the cosmos, absorb matter and energy with an insatiable hunger, seemingly destroying information in their relentless gravitational pull. Yet, according to the laws of quantum mechanics, information cannot simply vanish into the abyss. It must be preserved, encoded in some form, lurking in the shadows of the universe. This tension between general relativity and quantum mechanics gives rise to one of the most perplexing questions in modern physics: the information paradox. The paradox emerged from the work of Stephen Hawking, who in 1974 proposed that black holes are not entirely black, but emit thermal radiation, now known as Hawking radiation. This radiation, he argued, carries energy away from the black hole, causing it to slowly evaporate over trillions of years. But if a black hole evaporates completely, what happens to the information it swallowed? Does it disappear with the black hole, or is it somehow encoded in the Hawking radiation? Observation. Quantum mechanics forbids information loss. This principle, known as the conservation of information, is a cornerstone of modern physics. It implies that the information about a system, whether it's a star, a planet, or a single atom, can never truly be destroyed. It may be transformed, scattered, or hidden, but it must always exist in some form. If information were lost in a black hole, it would violate this fundamental law. Interpretation. Stephen Hawking himself grappled with this problem throughout his career. In 2004, he proposed a potential solution. Information might be stored at the event horizon, the boundary from which nothing, not even light, can escape. According to this idea, the information is not destroyed, but instead encoded in subtle fluctuations of the Hawking radiation. However, this hypothesis remains unproven and is still a subject of intense debate among physicists. Speculation. Could black holes violate fundamental laws of physics? If information is not preserved, it would challenge the very foundations of quantum mechanics. Some researchers have proposed radical alternatives, such as the idea that black holes are not singularities but instead portals to other universes. Others suggest that information might remain trapped within the black hole, hidden from our view but not destroyed. These ideas push the boundaries of our understanding, forcing us to confront the limits of human knowledge. The information paradox challenges our understanding of gravity and quantum mechanics, two pillars of modern science. It highlights the deep incompatibility between these theories, which describe the universe at vastly different scales. General. Relativity, which governs the behavior of massive objects like stars and galaxies, cannot reconcile with quantum mechanics, which explains the behavior of particles at the smallest scales. The paradox forces us to question whether these theories are incomplete or if there is a deeper, unifying framework waiting to be discovered. The paradox also has profound implications for our understanding of time. In the strange world of black holes, time slows down as one approaches the event horizon, a phenomenon known as gravitational time dilation. For an outside observer, an object falling into a black hole appears to freeze in time, never quite crossing the boundary. Yet, from the perspective of the object itself, time flows normally, and it passes through the horizon without noticing anything unusual. This disconnect between perspectives raises further questions about the nature of time and how it is intertwined with the fate of information. Perhaps the most intriguing aspect of the information paradox is its connection to the concept of entropy, a measure of disorder in a system. According to the second law of thermodynamics, entropy always increases over time, reflecting the natural tendency of systems to become more disordered. Black holes, however, seem to defy this law. They have an enormous amount of entropy, yet they appear to be completely orderly, with no internal structure or complexity. This contradiction has led some physicists to propose that black holes might be the ultimate repositories of entropy, holding the keys to understanding the universe's evolution. Recent developments in theoretical physics have offered new insights into the information paradox. In 2019, researchers proposed the concept of islands, regions of space-time where information from inside a black hole can be accessed. This idea, based on the holographic principle, suggests that the information about a black hole's interior is somehow encoded on its surface, much like a three-dimensional image can be projected from a two-dimensional hologram. While this theory is still in its early stages, it offers a tantalizing glimpse into how the paradox might be resolved. The information paradox remains unresolved, a critical puzzle in modern physics. It stands as a testament to the mysteries of the cosmos and the limits of human understanding. As we continue to explore the depths of the universe, the paradox challenges us to rethink our most fundamental assumptions about reality. Whether through new theories, experiments, or unexpected discoveries, the quest to solve the information paradox will undoubtedly shape the future of science and our place in the cosmos. Part 11. The Multiverse Hypothesis. Are there other universes? Mathematical models suggest that our universe might be just one of many. Observation. Infinite space allows for repeating structures, including copies of our world. Picture this. If the cosmos stretches infinitely in all directions, the probability of another Earth, or even another you, becomes not just possible but statistically inevitable. Imagine gazing into the night sky, knowing that somewhere out there, beyond the furthest reaches of our observable universe, another version of this moment might be unfolding. In a cosmos that spans at least 93 billion light-years in diameter, the sheer scale of existence makes the idea of multiple universes seem almost plausible. Interpretation. The multiverse hypothesis proposes parallel universes with varying physical laws. Some theories suggest that these universes might coexist in higher dimensional space, invisible to us, but just as real. For instance, the many worlds interpretation of quantum mechanics posits that every possible outcome of a quantum event spawns a new, separate universe. In this framework, there could be universes where dinosaurs never went extinct, where humanity never evolved, or where the laws of physics themselves are rewritten. One model, known as the inflationary multiverse, suggests that during the rapid expansion of the early universe, bubbles of space-time inflated into separate, self-contained universes, each with its own unique properties. Speculation. Could we ever detect evidence of another universe? Some scientists propose that collisions between universes could leave faint imprints on the cosmic microwave background radiation, the afterglow of the Big Bang. These imprints, if detected, might appear as circular patterns in the sky, like ripples on the surface of a pond. However, such signals would be incredibly faint, buried beneath layers of cosmic noise, and distinguishing them from ordinary astrophysical phenomena would be a monumental challenge. For example, the Planck satellite, launched in 2009, mapped the cosmic microwave background with unprecedented precision, yet it found no conclusive evidence of multiverse signatures. The multiverse is a profound speculation, pushing the boundaries of science and philosophy. It forces us to confront questions about reality, identity, and existence itself. If the multiverse is real, it means that our universe, with all its wonders and mysteries, is just one chapter in an infinitely vast cosmic library. Each universe would be a unique story, shaped by its own laws and histories, yet connected by the shared fabric of existence. In some theories, these universes might interact or influence one another through subtle gravitational effects, leaving traces that advanced civilizations could one day decipher. The multiverse hypothesis is purely theoretical, with no observational evidence. Despite its appeal, the multiverse remains a conceptual framework, untethered from empirical data. Critics argue that without testable predictions, the multiverse is more philosophy than science. Yet, its proponents counter that the limits of human observation should not constrain our understanding of the cosmos. After all, many groundbreaking ideas, from black holes to dark matter, began as speculation before becoming scientific fact. The Large Hadron Collider, for instance, was built to probe the fundamental nature of reality, and while it has not yet revealed evidence of the multiverse, its ongoing experiments continue to push the frontiers of physics. For now, the multiverse remains a tantalizing mystery, a reminder that our understanding of the universe is incomplete. It challenges us to look beyond our narrow slice of reality and imagine what lies beyond the edge of the known. Perhaps one day, with the help of advanced technology or a revolutionary breakthrough, we will catch a glimpse of another universe, a cosmic neighbor hidden in the vast expanse of the multiverse. Until then, the question lingers: are we alone in the cosmos, or are there other worlds waiting to be discovered? In the meantime, physicists and philosophers alike continue to explore the implications of the multiverse, debating its potential to redefine our place in the grand tapestry of existence. Part 12. The Birth of Stars. How are stars born? In the vast, frigid expanses of interstellar space, stars begin their lives as little more than whispers of hydrogen and helium, scattered among the dusty remnants of previous stellar generations. These diffuse clouds of gas and dust, known as molecular clouds, can stretch across dozens of light years, their masses sometimes exceeding millions of times that of our Sun. Within these clouds lie the seeds of future stars waiting for the slightest nudge to begin their journey toward ignition. Stars form from collapsing clouds of gas and dust, a process that unfolds over millions of years. Observation. Molecular clouds such as the Orion Nebula, located some 1,344 light-years away, are stellar nurseries teeming with infant stars. Infrared observations reveal these clouds as intricate tapestries of glowing filaments, where dense clumps of matter contract under their own gravity. These clumps, known as protostars, grow hotter and denser as they accrete more material, their cores reaching temperatures of millions of degrees. At this critical juncture, nuclear fusion ignites, and a new star is born. Interpretation: gravity is the architect of stars, compressing matter until the immense pressure and heat spark thermonuclear reactions. These reactions fuse hydrogen atoms into helium, releasing energy that counteracts the crushing. Force of gravity establishing a delicate balance that defines a star's life. Speculation: could the first stars have formed differently in the early universe? In the aftermath of the Big Bang, the universe was a simpler place, composed almost entirely of hydrogen and helium. Without the heavier elements that enrich modern molecular clouds, the first stars, known as population 3 stars, may have formed from pristine clouds of primordial gas. These stars were likely massive, short-lived and incredibly luminous, their intense radiation ionizing the surrounding gas and shaping the early cosmos. Their deaths in cataclysmic supernovae seeded the universe with the first heavy elements, paving the way for the formation of future generations of stars and, ultimately, planets like ours. The birth of a star is not a solitary event. Stars often emerge in clusters, sometimes containing thousands of members bound together by their shared gravitational pull. These clusters, such as the Pleiades or the Trapezium cluster in the Orion Nebula, are cosmic families where stellar siblings influence each other's growth and evolution. In dense clusters, close encounters between stars can disrupt their development, stripping away material or even leading to mergers that create massive, short-lived stars. These interactions shape the dynamics of star formation, influencing the lifespans and fates of entire stellar populations. Stars are the engines of creation, forging elements and shaping galaxies. Within their fiery cores, stars fuse hydrogen into helium, and later, in more massive stars, helium into carbon, oxygen, and heavier elements. These elements, scattered into space by stellar winds and supernova explosions, enrich the interstellar medium, providing the raw materials for new stars and planets. Over billions of years, this cycle of birth and death has transformed galaxies, turning them from barren collections of gas and dust into vibrant ecosystems teeming with stars, planets, and perhaps even life. The process of star formation is not always efficient. For every star that ignites, there are countless failed attempts, clumps of matter that never quite reach the critical mass or density needed to spark fusion. These failed stars, known as brown dwarfs, are intriguing objects that straddle the boundary between planets and stars. Though they lack the mass to sustain nuclear fusion, they still emit a faint glow, powered by the heat of their own contraction. Their study offers insights into the complex interplay of forces that govern star formation. Despite our understanding of star formation, mysteries remain. The first stars born in the early universe left no direct traces of their existence. Their properties and lifespans are inferred from theoretical models and simulations, but direct observation remains elusive. Future telescopes, such as the James Webb Space Telescope, may one day peer into the distant past, catching a glimpse of these elusive objects as they ignite in the cosmic dawn. Until then, the birth of the first stars remains one of astronomy's greatest enigmas. Part 13. The Death of Stars. How do stars die? This question has captivated astronomers for centuries, as the death of stars is not a singular event but a varied and spectacular process, deeply tied to their mass and composition. To understand this cosmic finale, we must first grasp the delicate balance that sustains a star throughout its life. At the heart of every star lies a fiery furnace, where nuclear fusion transforms hydrogen into helium, releasing energy that radiates outward, counteracting the crushing force of gravity. This equilibrium, however, is not eternal. A star's fate depends on its mass. For low-mass stars, those roughly the size of our Sun or smaller, the end is relatively peaceful. Observation: as these stars exhaust their hydrogen fuel, they transition into red giants, swelling to hundreds of times their original size. Their outer layers drift into space, forming planetary nebulae, glowing shells of gas and dust that stretch light years across. What remains is a white dwarf, a dense Earth-sized core of carbon and oxygen, slowly cooling over billions of years. These stellar remnants are incredibly compact. A teaspoon of white dwarf material would weigh as much as a large truck on Earth. For massive stars, those more than 8 times the mass of the Sun, the end is far more dramatic. Observation: these giants burn through their fuel rapidly, their cores collapsing under immense gravitational pressure. When the core can no longer sustain nuclear fusion, the star implodes in a fraction of a second, rebounding in a catastrophic explosion known as a supernova. These events are so powerful that they outshine entire galaxies for days or weeks. A single supernova can release as much energy in an instant as the Sun will emit over its entire 10 billion year lifespan. Interpretation: supernovae play a critical role in the cosmic ecosystem, seeding the universe with elements essential for life. The explosion forges heavy elements like iron, gold, and uranium, scattering them into space where they become the building blocks of new stars, planets, and even living organisms. The iron in our blood, the calcium in our bones, and the gold in our jewelry were all created in the fiery deaths of distant stars. Without supernovae, the universe would be a far less complex and diverse place. Speculation: could some stars avoid death entirely? While most stars will eventually succumb to their fate, some theoretical models suggest that under extremely rare conditions, a star might evade its end. For example, some researchers propose that a star could be rejuvenated through a collision with another star or by accreting matter from a companion, replenishing its fuel supply and extending its life. However, such scenarios are highly speculative and remain unproven. The life cycle of stars is a cosmic drama, shaping the evolution of the universe. From the quiet fading of a white dwarf to the explosive violence of a supernova, each death contributes to the ongoing story of the cosmos. These events not only create the raw materials for future generations of stars and planets, but also provide astronomers with invaluable clues about the universe's past and future. For instance, the distribution of supernova remnants in a galaxy can reveal its star formation history, while the presence of certain isotopes in meteorites on Earth points to nearby supernovae that influenced the early solar system. Star deaths are observed and classified, but rare phenomena remain unexplained. For example, astronomers have detected peculiar supernovae that defy conventional models, such as hypernovae that release 10 times more energy than typical supernovae. These events challenge our understanding of stellar evolution and may hint at entirely new processes at work in the universe. Additionally, the recent discovery of zombie stars, Stars that appear to survive partial supernova explosions has added another layer of mystery to the study of stellar death. As telescopes and simulations grow more advanced, scientists hope to unravel these cosmic enigmas and deepen our understanding of the universe's most spectacular events. Part 14. The Search for Life. Are we alone in the universe? This question has haunted humanity for centuries, driving us to explore the farthest reaches of the cosmos. The search for life beyond Earth is not just a scientific endeavor. It is a deeply human quest to understand our place in the universe and whether we are the sole inhabitants of a vast, silent expanse. Exoplanets orbiting distant stars offer tantalizing possibilities for life. Observation. As of 2023, over 5,000 exoplanets have been discovered, with a significant number located within the habitable zones of their stars. These zones, often referred to as the Goldilocks zones, are regions where temperatures could allow for liquid water to exist on the surface, a critical ingredient for life as we know it. Interpretation. Life requires specific conditions, but the universe is vast and diverse. The sheer number of exoplanets suggests that the conditions necessary for life may not be as rare as once thought. Speculation. Could life exist in forms beyond our imagination, thriving in environments we consider inhospitable? The search for extraterrestrial life is a quest to understand our place in the cosmos, and every new discovery brings us closer to unraveling this profound mystery. One of the most promising exoplanets is TRAPPIST-1F, located approximately 40 light-years away in the constellation Aquarius. This Earth-sized planet orbits within the habitable zone of its star, TRAPPIST-1, a red dwarf much cooler and smaller than our Sun. TRAPPIST-1F is part of a system of 7 Earth-sized planets, 3 of which lie in the habitable zone. The proximity of these planets to one another creates a breathtaking celestial dance, where neighboring worlds appear larger in the sky than our moon does to us. This system offers a unique opportunity to study multiple, potentially habitable worlds in a single star system, providing a laboratory for understanding the diversity of life in the universe. The search for life is not limited to distant exoplanets. Within our own solar system, moons like Enceladus and Europa have captivated scientists with their subsurface oceans of liquid water. Enceladus, a moon of Saturn, ejects plumes of water vapor and ice particles from its southern polar region, hinting at a vast ocean beneath its icy crust. Europa, orbiting Jupiter, is believed to harbor a global ocean up to 100 kilometers deep, heated by tidal forces from the gas giant. These oceans, shielded from harmful radiation by thick layers of ice, could provide the stable environments necessary for life to emerge. Missions like NASA's Europa Clipper and the European Space Agency's JUICE, Jupiter Icy Moons Explorer, aim to explore these worlds in the coming decade, seeking signs of life in the chemical signatures of their oceans. On Mars, the search for life has focused on the planet's ancient past. Observation. Mars once had abundant liquid water on its surface, as evidenced by dried-up riverbeds, deltas, and lake basins. The Curiosity rover discovered evidence of a lake that existed billions of years ago in Gale Crater, where conditions may have been suitable for microbial life. Interpretation. While Mars is now a cold and desolate world, its past offers a window into a time when it may have been habitable. Speculation. Could life have arisen on Mars during its warmer, wetter period? And could remnants of that life still exist today, hidden beneath the surface or in pockets of liquid water? The Perseverance rover, currently exploring Jezero crater, is collecting samples of Martian rock and soil that will be returned to Earth in the 2030s. These samples could contain the first definitive evidence of extraterrestrial life, revolutionizing our understanding of biology and the universe. No definitive evidence of extraterrestrial life has been found, but the search continues. With each new discovery, from exoplanets to the oceans of distant moons, we inch closer to answering the question that has captivated humanity for millennia. Are we alone? The quest for life beyond Earth is not just about science. It is about our collective desire to know whether we share the universe with other beings, and what that might mean for our future among the stars. Part 15. The Fermi Paradox. Where are the aliens? This question, posed by physicist Enrico Fermi in 1950, has haunted scientists and thinkers for decades. The sheer scale of the cosmos is staggering. With an estimated 100 billion stars in the Milky Way galaxy alone, and at least as many planets, the mathematical probability of intelligent life emerging elsewhere seems overwhelmingly high. Yet, as we scan the skies with increasingly sophisticated technology, we are met with a deafening silence. Observation. We see no clear signs of advanced civilizations, no radio signals, no engineered structures, no unambiguous evidence of extraterrestrial technology. The absence of contact or detection has become one of the most profound mysteries in modern science. The Fermi Paradox forces us to confront unsettling possibilities. Interpretation. Perhaps civilizations inevitably destroy themselves through war, environmental collapse, or technological catastrophe. Humanity's own history offers a sobering example. In the 20th century alone, we developed nuclear weapons capable of global annihilation, and our industrial activities have accelerated climate change, threatening the planet's habitability. If this pattern holds true for other intelligent species, it could explain the eerie quiet of the cosmos. Alternatively, advanced civilizations might intentionally avoid contact, adhering to a kind of prime directive to prevent disruption of less advanced cultures. Or they may have transcended biological existence entirely, merging with technology or evolving into forms unrecognizable to us. Speculation. Could we be living in a cosmic simulation? This idea, popularized by philosopher Nick Bostrom, suggests that what we perceive as reality might be an artificial construct created by a far more advanced civilization. If true, it would explain why we have yet to detect other life. Our simulated universe may be designed to appear empty, or our simulators may have chosen to conceal their presence. Another possibility is that intelligent life is extraordinarily rare, a product of such specific and unlikely conditions that it has only occurred once in the observable universe. This rare Earth hypothesis points to the delicate balance of factors that allowed life to flourish on. Our planet, from our stable orbit to the presence of a large moon and a protective magnetic field, the search for extraterrestrial intelligence, SETI, has been ongoing since the 1960s, with scientists using radio telescopes to listen for signals from distant stars. The most famous of these efforts, the SETI Home Project, harnessed the computing power of millions of volunteers to analyze data from the Arecibo Observatory in Puerto Rico. Despite decades of effort, no definitive evidence of alien communication has been found. The silence has led some researchers to propose that advanced civilizations might communicate in ways we cannot yet comprehend, using technologies far beyond our current understanding. For example, they might use neutrinos, gravitational waves, or even quantum entanglement to transmit information instantaneously across vast distances. Another intriguing theory is the zoo hypothesis, which suggests that advanced civilizations are aware of us but have chosen to observe us from a distance, much like scientists studying a delicate ecosystem. This idea implies that such civilizations possess not only incredible technological prowess, but also a high degree of ethical restraint. However, the lack of evidence for this hypothesis makes it difficult to test, leaving it in the realm of speculation. The Fermi Paradox also raises questions about the nature of intelligence itself. What if the forms of life we are searching for are so alien that we fail to recognize them? For instance, an intelligent species might exist as a distributed network of microorganisms communicating through chemical signals rather than electromagnetic waves. Or they might inhabit the interstellar void, harnessing energy from stars and using dark matter as a medium for communication. The possibilities are as vast as the universe itself, challenging our human-centric understanding of what constitutes life and intelligence. The Fermi Paradox remains unresolved, fueling speculation about extraterrestrial life. As our technology advances and our understanding of the cosmos deepens, we continue to listen, to search, and to wonder. Perhaps one day we will detect a signal, a whisper from the stars that proves we are not alone. Or perhaps we will discover that the silence is not empty but full of mysteries waiting to be unraveled. Until then, the question persists. Where are the aliens? Part 16. The nature of time. Is time a fundamental force? Time flows differently in strong gravitational fields as predicted by general relativity. This phenomenon, known as gravitational time dilation, has been experimentally verified with stunning precision. For instance, atomic clocks placed at different altitudes on Earth tick at slightly different rates due to variations in gravity. At sea level, clocks run slower than those at higher elevations. The effect is subtle, but measurable. A clock on the surface of Earth will lose about 2.5 milliseconds every 30 years, compared to one at an altitude of 30,000 feet. This phenomenon is not just a theoretical curiosity, it has practical applications in modern technology, such as the Global Positioning System, GPS, which relies on correcting for time dilation to provide accurate location data. Without accounting for both gravitational and velocity-based time dilation, GPS, errors would accumulate at a rate of about 10 kilometers per day, rendering the system useless. Observation. Clocks run slower near massive objects. Interpretation. Gravitational time dilation is confirmed experimentally. The Hafel-Keating experiment in 1971 provided one of the earliest direct tests of this effect. Scientists synchronized several highly accurate cesium beam atomic clocks and then flew some of them around the world on commercial airliners. Upon returning, the clocks that had travelled gained a few hundred nanoseconds compared to the stationary ones. This result aligned perfectly with the predictions of general relativity, combining the effects of gravitational time dilation and the faster motion of the airborne clocks. Such experiments have since been refined, and today time dilation is routinely observed in particle accelerators like the Large Hadron Collider, LHC, where particles moving close to the speed of light experience time more slowly than stationary observers. Speculation. Could time be an emergent property of deeper physical laws? And the nature of time is a profound mystery, intertwined with the fabric of space-time. Some theoretical physicists suggest that time might not be a fundamental aspect of the universe, but rather a byproduct of more fundamental processes. For example, in loop quantum gravity, time is not treated as an absolute continuous flow, but as a discrete, granular structure at the Planck scale, approximately 10 moles to 43 seconds. In this framework, time could emerge from the complex interactions of quantum loops that make up space-time. Similarly, string theory posits that time might be a consequence of the vibrational states of one-dimensional strings that underpin all matter and energy. These theories remain highly speculative, but they offer tantalizing glimpses into the possibility that time is not what it seems. Beyond the realm of physics, time permeates our human experience in ways that are both profound and mundane. It shapes our perception of reality, our memories, and our sense of self. Psychologists have long studied how our brains interpret time, revealing that our subjective experience of its passage can be highly variable. For instance, time appears to slow down in moments of danger or stress, a phenomenon often reported by survivors of accidents or traumatic events. Conversely, time seems to accelerate as we age, with years feeling shorter and memories blurring together. This psychological elasticity of time adds another layer of complexity to our understanding of its nature. The enigma of time extends into cosmology as well. The arrow of time, which points inexorably from the past to the future, remains one of the greatest unsolved problems in science. While the laws of physics are largely time-symmetric, meaning they work the same forward and backward, our experience of time is decidedly one-directional. This asymmetry is closely tied to the concept of entropy, a measure of disorder in a system. According to the second law of thermodynamics, entropy always increases over time in a closed system, creating a distinction between past and future. However, the origin of this arrow of time is still debated. Some theories propose that it emerged from the low entropy state of the early universe, a mysterious condition that allowed the cosmos to evolve into its current, highly structured form. Time dilation is observed, but the fundamental nature of time remains uncertain. Despite our ability to measure and manipulate time with ever-increasing precision, its true essence eludes us. Is time a fundamental building block of the universe, or is it a construct that arises from deeper, more abstract principles? As our understanding of physics continues to evolve, so too will our grasp of time, perhaps revealing it to be something far stranger and more profound than we ever imagined. Part 17. The Edge of the Universe. What lies beyond the observable universe? This question has captivated scientists and philosophers for centuries, pushing the boundaries of human imagination and technological capability. The observable universe, a vast sphere of galaxies, stars, and cosmic phenomena, is limited by the speed of light and the age of the cosmos. Observation. We can only see as far as light has travelled since the Big Bang, approximately 13.8 billion years ago. This means our cosmic horizon stretches about 46 billion light-years in all directions, a seemingly paradoxical figure due to the universe's expansion during light's journey. Interpretation. Beyond this horizon lies unseen space, potentially infinite and forever hidden from our view. Speculation. Could the universe extend forever, a boundless expanse of matter and energy, or does it have an edge, a cosmic cliff beyond which nothing exists? The cosmic horizon is more than just a boundary of visibility. It is a boundary of knowledge, hiding the universe's true extent and structure. To grasp the scale of the observable universe, consider this. If the Earth were scaled down to the size of a single grain of sand, the observable universe would stretch over 20 kilometers across. Within this unfathomable volume, astronomers estimate there are at least 100 billion galaxies, each containing hundreds of billions of stars on average. Yet this is only the universe we can detect. The unobservable universe, if it exists, could dwarf this scale, teeming with galaxies and phenomena we will never perceive. Some theories suggest that the universe is not just vast, but infinite, with no edge or boundary. However, other models propose a finite universe, curved in higher dimensions like the surface of a sphere, where traveling in one direction would eventually bring you back to your starting point. The nature of the universe's edge, if it exists, is one of the greatest mysteries in cosmology. If the universe is finite, what lies beyond its boundary? Some speculate that it could be a void of nothingness, a place where the laws of physics as we know them cease to exist. Others propose that our universe is just one of many in a vast multiverse, each with its own set of physical laws and constants. In this scenario, the edge of our universe might be a membrane-like barrier separating us from other realities. However, these ideas remain purely speculative, as we currently have no way to observe beyond our cosmic horizon. The observable universe is defined by a radius of 46 billion light-years, but its full size and structure remain unknown. Despite advancements in telescope technology and theoretical physics, the edge of the universe, whether it exists or not, remains beyond our reach. The Hubble Space Telescope, launched in 1990, has allowed us to peer deeper into the cosmos than ever before, revealing galaxies formed just a few 100 million years after the Big Bang. The James Webb Space Telescope, launched in 2021, promises to push this boundary even further, probing the earliest moments of star and galaxy formation. Yet even these instruments are confined to the observable universe, leaving the question of what lies beyond a matter of speculation. The quest to understand the edge of the universe is not just an academic pursuit. It speaks to the human desire to explore and comprehend the unknown. Every civilization throughout history has gazed at the night sky and wondered what lies beyond the visible stars. Today we stand on the shoulders of giants, armed with telescopes and theories that allow us to see further and understand more than ever before. Yet the edge of the universe remains a frontier, a reminder that our knowledge, like our sight, has limits. Whether the universe is infinite or bounded, its true nature may forever elude us, a cosmic enigma that defines the limits of human understanding. Part 18. The Fine-Tuning Problem. Why is the universe suited for life? This question, though simple, lies at the heart of one of the most profound mysteries in modern cosmology. The fundamental constants of nature, such as the strength of gravity, the mass of the electron, and the force-binding atomic nuclei, are delicately balanced, like a cosmic scale, to allow for the formation of stars, planets, and ultimately, life itself. Observation. Even the slightest deviation in these constants would render the universe unrecognizable and inhospitable to life as we know it. For instance, if the strong nuclear force were just 2% weaker, the universe would consist solely of hydrogen, with no heavier elements to form complex structures. Conversely, if it were slightly stronger, stars would burn out too quickly for life to evolve. The fine-tuning problem is not limited to a single constant, but extends across the entire fabric of the cosmos. The ratio of the electromagnetic force to gravity is a staggering 10, 14, an almost unimaginably large number, Yet this ratio is essential for the stability of stars like our Sun, which provide the energy necessary for life. If gravity was stronger, stars would burn hotter and faster, exhausting their fuel in a fraction of the time it took our Sun to support the evolution of life on Earth. On the other hand, if gravity were weaker, stars would struggle to form at all, leaving the universe a cold and lifeless expanse. Interpretation. This fine-tuning could be a remarkable coincidence, an outcome of chance in the vast lottery of cosmic possibilities. Alternatively, it could signify the existence of deeper laws of physics, principles that constrain the values of these constants in ways we have yet to understand. Some scientists propose that fine-tuning is a clue pointing toward a unified theory. A theory of everything that would explain these constants as natural consequences of underlying physical processes. However, such a theory remains elusive, despite decades of intense theoretical and experimental effort. Speculation. Could the multiverse explain fine-tuning? In this provocative scenario, our universe is just one of countless others, each with its own unique set of constants and laws. If the multiverse is real, it could explain why our universe appears so finely tuned. It is simply one of the few universes capable of supporting life, and we exist in it because we could not exist anywhere else. This idea, while speculative, has gained traction in theoretical physics, as it offers a potential solution to the fine-tuning problem without requiring a deeper understanding of the constants themselves. However, the multiverse hypothesis is not without its critics. Many argue that it is untestable and therefore unscientific, as it relies on the existence of universes we can never observe or interact with. Others point out that the multiverse, if it exists, would introduce new mysteries of its own. For example, why does the multiverse generate universes with such a wide range of properties? And what, if anything, governs the distribution of these properties across the multiverse? Despite these debates, the fine-tuning problem remains a central puzzle in cosmology. It challenges our understanding of the universe's underlying principles and forces us to confront the limits of our knowledge. Every time we look up at the night sky, we are reminded of the delicate balance that allows us to exist, a balance that science has yet to fully explain. The fine-tuning problem is not just a scientific curiosity, it is a window into the deepest questions about the nature of reality and our place within it. Fine-tuning is observed but unexplained, a profound mystery in cosmology. While the problem has inspired bold theories and speculations, it remains one of the greatest unsolved puzzles in our quest to understand the universe. Part 19. The Future of Discovery. What will we learn next? Modern telescopes and detectors push the boundaries of observation, revealing the universe in ways once thought impossible. The James Webb Space Telescope, with its 6.5-meter gold-plated mirror, can detect infrared light from the earliest galaxies formed just a few 100 million years after the Big Bang. Its first images, released in July 2022, revealed galaxies so distant that their light has taken over 13 billion years to reach us. One such galaxy, GLASS Z13, is now the most distant known galaxy, offering a glimpse into the universe when it was just 300 million years old. Observation. The James Webb Space Telescope peers into the distant past, unveiling the universe's infancy, and has identified chemical signatures in the atmospheres of exoplanets, hinting at the potential for habitability beyond our solar system. These technological marvels are not limited to space. On Earth, the Event Horizon Telescope, a global network of radio observatories, captured the first ever image of a black hole in 2019, This feat required synchronizing data from 8 telescopes spread across 4 continents, resulting in a virtual Earth-sized dish. The image of the supermassive black hole at the center of galaxy M87, 55 million light-years away, confirmed predictions of Einstein's general relativity under extreme conditions. In 2022, the collaboration released an image of Sagittarius AC, the black hole at the heart of our own Milky Way galaxy, offering an unprecedented view of the gravitational monster lurking just 26,000 light-years away. Interpretation. New data will refine our understanding of the universe's history, from the violent dance of black holes to the subtle whispers of cosmic dawn. The upcoming Next Generation Very Large Array, NGVLA, set to begin construction. In 2026, will provide even sharper images of black holes and other cosmic phenomena operating at frequencies up to 116 GHz. Yet every answer spawns new questions. Speculation. Could future discoveries rewrite the laws of physics? The search for dark matter, which constitutes 85% of the universe's mass but interacts with light only through gravity, remains one of the greatest challenges in modern astrophysics. Experiments like the Large Hadron Collider at CERN and the Xenon 1T detector in Italy have narrowed down the possibilities, but dark matter particles continue to evade detection. Theoretical models propose candidates such as WIMPs, weakly interacting massive particles, or axions, but conclusive evidence remains elusive. The upcoming Darwin mission, a proposed space-based gravitational wave observatory, aims to detect primordial gravitational waves generated during the inflationary epoch, mere fractions of a second after the Big Bang. This could provide indirect evidence of dark matter interactions during the universe's earliest moments. The quest for knowledge is an endless journey driven by curiosity and innovation. Consider the Breakthrough Starshot initiative, announced in 2016, which aims to send a fleet of tiny spacecraft to the Alpha Centauri star system, 4.37 light-years away. Propelled by lasers, these nanocraft could reach speeds of up to 20% the speed of light, making the journey in just 20 years. This ambitious project, though still in its early phases, exemplifies humanity's relentless drive to explore the unknown. If successful, Starshot could capture the first close-up images of Proxima Centauri b, an Earth-sized exoplanet orbiting within the habitable zone of its star. Technology advances, but the universe's mysteries remain vast and uncharted. The Kepler Space Telescope, launched in 2009, revolutionized our understanding of exoplanets, discovering over 2,600 confirmed worlds beyond our solar system. Its successor, TESS, Transiting Exoplanet Survey Satellite, launched in 2018, has already identified thousands more candidates. Each new exoplanet raises questions about habitability, biosignatures, and the possibility of life elsewhere in the cosmos. The upcoming Plato mission, scheduled for launch in 2026, will search for Earth-like planets in the habitable zones of Sun-like stars, further expanding our catalogue of potential worlds. As our tools grow more sophisticated, so too do the enigmas they uncover. The cosmos is a tapestry of paradoxes, each one a thread in the story of creation. From the dark sky to the enigmatic pull of dark matter and energy, from the birth of stars to the fate of the universe, every mystery beckons us deeper. Into the Abyss, the Gaia mission, launched by the European Space Agency in 2013, is mapping the Milky Way in unprecedented detail, tracking the positions and velocities of over 1 billion stars. This data has revealed the galaxy's dynamic history, including past collisions with smaller galaxies and the rippling effects of dark matter's gravitational influence. Gaia's most recent data release, DR3, includes detailed chemical compositions of stars, providing clues about their birthplaces and evolution. As we unravel the cosmic enigma, we confront not just the mysteries of space, but the very limits of human comprehension. The Vera C. Rubin Observatory, scheduled to begin operations in 2024, will conduct a 10-year survey of the southern sky, capturing images of billions of galaxies and stars. Its legacy survey of space and time, LSST, will create the deepest, widest view of the universe too. Date: probing the nature of dark energy and exploring the transient sky. With each discovery, we inch closer to understanding the universe's profound complexity. The observatory's 8.4-meter mirror will allow it to detect even faint supernovae in distant galaxies, shedding light on the accelerating expansion of the universe. The search for truth is endless, but it is the journey itself that defines us. In the vast, silent expanse of the cosmos, humanity stands as a beacon of curiosity, forever reaching for the stars. The upcoming Square Kilometre Array, SKA, a global radio telescope project, will combine signals from thousands of dishes across Australia and South Africa. When fully operational in the 2030s, it will be 50 times more sensitive than any existing radio instrument, capable of detecting the faint signals from the universe's first stars and galaxies. This cosmic dawn occurred roughly 100 million years after the Big Bang, marking the end of the cosmic dark ages and the birth of structure in the universe. The SKA will also search for signs of extraterrestrial intelligence, scanning millions of star systems for technosignatures, evidence of advanced civilizations. Its mid-frequency component, SKA-mid, will be able to detect pulsars and fast radio bursts, FRBs, from other galaxies, offering insights into the extreme physics of neutron. Stars. And so, the greatest mystery of all remains. Where will our journey take us next? In the coming decades, new observatories and experiments will continue to push the boundaries of our knowledge. The Einstein telescope, a proposed third-generation gravitational wave detector, will be capable of detecting mergers of black holes and neutron stars throughout the observable universe. Its underground design and cryogenic technologies will allow it to detect gravitational waves at frequencies as low as 1 Hz, providing unprecedented sensitivity to cosmic events. Meanwhile, the Roman Space Telescope, set to launch in the mid-2020s, will conduct a wide-field infrared survey of the universe, exploring the nature of dark energy and searching for rogue planets wandering the interstellar void. With each new instrument, we expand our cosmic horizons, venturing ever further into the unknown. The future of discovery lies not just in observing the cosmos, but in understanding its fundamental laws. Theoretical physicists are exploring models of string theory, which proposes that the fundamental particles of the universe are not point-like dots, but one-dimensional strings vibrating at specific frequencies. These models suggest the existence of extra dimensions beyond the familiar four of space-time, potentially explaining phenomena like dark matter and the accelerating expansion of the universe. Experiments like the Laser Interferometer Space Antenna, LISA, set to launch in the 2030s, could detect gravitational waves from cosmic strings, hypothetical defects in space-time predicted by string theory. As we probe deeper into the fabric of reality, we may find that the universe is even stranger and more wondrous than we ever imagined. But the future of discovery also lies in the hands of the next generation of scientists, engineers, and dreamers. Programs like NASA's Artemis mission, which aims to return humans to the moon by 2025, inspire young minds to pursue careers in science and exploration. The Artemis program will establish a sustainable human presence on the lunar surface, paving the way for future missions to Mars and beyond. As we venture outward into the solar system, we carry with us the spirit of discovery that has defined humanity since the dawn of civilization. The journey is endless, but with each step we come closer to understanding our place in the cosmos. In the end, the future of discovery is not just about what we find, but about who we become in the process. It is about the courage to ask questions, the humility to admit what we do not know, and the determination to seek answers no matter how distant or elusive they may be. It is about standing on the shores of the cosmic ocean, gazing out at the vast expanse of the unknown, and daring to set sail. For it is in the journey, not the destination, that we find our true purpose: to explore, to question, to discover, and to dream. And so, with eyes turned skyward and hearts filled with wonder, we step into the future, ready to embrace the mysteries that await us in the cosmos.